30.
B is like the fraction.
Sure, okay, perfect. So, makes sense now. And your numbers matched up in your tables when you put them in.
Oh, I guess I didn't do that.
And obviously you have to, with x equals 0, you have to kind of think about it.
Yeah.
Because I didn't include that in the table.
Yeah,
I think we got it there. Yeah, you want to talk about it? Let's come back together and we'll see if we can come up with an equation to see what we can do. All right. So, for the area of one piece, what do you think? Let's look at our initial value. Let's think about our initial value first, which I think was okay. So in red, I'm gonna use the same notation I did, or same colors for it than as the slide as from earlier. Okay. So initial value of area. So what does our initial value represent? What does it mean? Yeah, Hillary?
The whole sheet of paper.
Okay. Yeah. So kind of it's the area of the whole sheet of paper when we don't do anything to it, right? When we don't make any cuts on it. Okay. Good. So what is given what we know about the sheet of paper, what is our initial value then? What's the initial area without any cuts being made? 96. Okay, good. So that'll be our initial value there. Okay. And what about a factor of that? What's it either increasing or decreasing by? So I think we kind of remember. I think all of you guys can tell that the area was going down each time, right? So it was getting cut in half. Okay. So how can we turn that into a decay factor or a factor that it's decreasing by? What would it be there in our equation? What do you guys come up with?
Would it just be 1/2?
1/2? Yeah, you're right. It would be. So I'm going to put it in parentheses. Just parentheses help me keep things memorized. And are we going to plug anything in for x here? Do we have a specific point or number we're trying to find there for y or x, or are we just kind of putting it in there and giving an equation? I'm sorry?
Just write x.
Just write x? Okay. Yeah, you're right. Good. So now we can kind of do this as an example. So let's pick, I don't know, what do you guys want to check to see if our equation's right? What number do you want to use? 3. So if we substitute x equals 3, okay, that means we get, so we have 96 times 1/2 to the 3rd equals y, okay? So that means that y equals 96 times, does anybody know what 1/2 to the 3rd is?
1/8.
Thank you for raising your hand, Hillary. Yes, it is 1/8, good, okay? Yes, so 96 times 1/8, okay?
Would I multiply 96 times 1/2 first?
No, we would not, but that's a very good question. Remember our order of operations is parentheses first, so we do everything inside parentheses, which 1/2, there's nothing to do to it. So we can move on to the next thing, which is e, which is exponents. So we have to apply that exponent, because that exponent of 3 is attached to that 1/2 value first, and then we can do the multiplication there. Okay, that makes sense?
Yeah.
Okay, so if we do 96 times 1/8, what does that tell us? What does that give us?
12.
12? Very good, yeah. So we have 12, I'm going to write inches squared, but we don't really need to do that. So if you look at your column, or your table there, you should have, if you plug it at 3 cuts, and you go over to your area column, you should have 12 inches. Does everybody have 12 inches there? Yes? Good. All right, so that must mean we have a correct equation. Okay?
Quick.
Yeah.
So then X would represent the number of cuts and tears, and then Y would represent the area.
Yeah, very good, yes. So maybe, I'll kind of write that as a good thing to point out. So our X is our number of cuts or tears, whatever you want to call it. Tears, not to be mistaken with tears. Spelled the same, said different. I'm a little English lesson. All right. Okay, good. And then, like you said, Stephen, Y is going to be our area of each piece. Okay. So now, growth or decay, is that growing exponentially or is it decaying exponentially? What do you guys think? Decaying? Yeah, everybody agree with that's decaying? Okay. So I'll just circle decay there.
It's weird because like X is always increasing, so
Yeah.
why does it get a smaller answer?
It's a good question. Because if you think about this, so we go from 1/2, right? Because this is our growth or decay factor, so which I kind of just told you. Okay. So when we find that, we have b equals 1/2, right? Okay. Because that's our decay factor. Now, if you think about this, as x increases, is our decay factor going to get bigger or smaller? Smaller. Why?
Plugged in a 3 there, it was 1/8.
It was 1/8,
1/8
and
is
you saw that
smaller.
1/8 is smaller than 1/2.
Yep.
Good. Okay. So that means that you're multiplying, or you're, I guess you could almost say, let's think about it this way. This might be easier to grasp. So you're, when you multiply by a small number, that's kind of saying, if you perform this multiplication, you actually get 96/8. You see that?
Mm-hmm.
Okay. So let's say x was 4 in this case. Okay. That would give us 96 times 1/16, right? Okay. So 96 divided by 16. So that number on the bottom is getting bigger and bigger. Okay. So now if we think about 96/8, and then we consider 96/, I saw somebody do that one time. Alright, so we have 96/8. And we have 96/16. How would you compare those? What do you guys think? Because think about if the number in the denominator is bigger, what's your final answer going to be? Smaller, right? It's going to keep getting smaller and smaller. Did I kind of see how does that make sense? How it gets smaller and smaller like that? Yeah. So 96/8 is actually going to be not greater than or equal to. That's not possible. But greater than. Good. But that's a very good question. Okay. So that's why it's decaying, even though x is getting bigger. X actually is it's your number of cuts. So you can't really take away any cuts if you think about it this way. You can never have a negative amount of cuts. Okay, you always have to have a positive number of cuts, and it's always going to be increasing. Okay. Good. Everybody good there? So now if we talk about number of pieces, what did you guys come up with an equation there? Anyone want to give it a shot? Let's talk about this. Or we can give you the whole equation. Go ahead.
Yeah, I got it.
Yeah, the whole equation?
Yeah, it's, well, it's 2 to the x, but 1 times 2 to the x.
Okay, so you have 2 to the x.
Yeah.
Good. And so our initial value is what in this case? What's our initial number of pieces if we made no cuts? 1? You guys said 1?
Yeah.
Yeah, good. Because we're not doing anything to it, we just have 1 piece of paper. But we all know that even when we do this exponent first, anything we get here multiplied by 1, not going to change anything, right? So that's why Stephen just said 2 to the x. So, very good. That's an x. Okay? Good. So that's our equation there. Now, again, we'll go through and double check that. What do we want to plug in? Do we want to plug in a 3 again to test the equation? Yeah? 4? All right, let's try 4. Let's change it up a little bit. Okay? So that means y, again, in this case, x is our number of tears again, right? Right cuts. Okay? And y is what? Number of pieces. Very good. Good. So if we're plugging in a 4 here for x, we're going to get 1 times 2 to the 4th. Okay? Anybody know what 2 to the 4th is? 2 times 2 is
4,
4 times 2 is
8,
8 times 2 is
16.
16. Very good. So we're at equals 1 times 16, which is 16. Thanks, Stephen. Good. All right. Now, so if we look at our column for number of pieces in our table, at y or at x equals 4, or at 4 cuts, do we have 16 total pieces? Is that what you guys found? Yeah? All right, looks like we did something right in our equation. So, very good. So either one of these is going to be correct. If you write 2 to the x, that's totally fine. If you were to write that on a test or a quiz, I wouldn't take off points for that. But if you wrote 1 times 2 to the x, same thing, you wouldn't lose any points. It's just a matter of how you like to picture it. Okay? So that is that. Does anybody have any questions about what we've talked about so far? No? Okay. I'm going to go back to your question earlier about, how much do you want time? 4 minutes? Perfect. All right. I'm going to go back to what Gian asked a question about earlier, is what about negative numbers? Okay? No, negative numbers even for A and B. Okay, so first with A, let's think about this. So if you had, does anybody have any examples where you would have a negative initial value? Maybe, oh, I got a good one. How about money? Okay, think about that. So let's say we start with a negative amount of money in an account. It's kind of hard to picture, but just bear with me there, okay? So if we have, that means our A in this case would be a negative number, okay? So is that, and then we have, is that going to change how our equation kind of interacts? Like if we had, let's say I started with negative $1,000 in my account, and I was adding in $100 every month, let's say. So think about it, so after 3 months, let's say, how much money would I have now in the account? So is that, you'd have what? 700?
Yeah, right, 1,000, what was it, negative 1,000,
Negative
and
1,000.
then 100 for each month,
Mm-hmm.
3 months?
Yeah, so I would have
Negative
1,000.
se-
Yeah,
negative.
negative 700, good. Because I'm adding in 100, wait,
But is that because you're multiplying, so wouldn't it stay negative?
yes, it would. So as, actually it was 3.
Yeah, negative 700.
Oh, yeah.
What, 1,000?
Yeah, yeah, because you would add, that's how much you would have at, so this would be 300 here. You would have added $300, no. Or, yeah, I guess,
Yeah,
like that.
300 and
Yeah,
it's negative
okay.
1,000.
Right, so you'd be adding in money. So really, your A can be whatever you want it to be. It's just kind of where you're starting, your number is starting. But let's think about B for a minute. If B is negative, we have already talked a little bit about, yes, Hillary.
But if you're multiplying 300 times negative 1,000, you're not gonna get negative 700.
Right. That example might not necessarily fit the exponential example. But that's just kind of the thing. That's kind of just the
It would
thing.
just be like negative 1,000 plus.
Yeah, it'd be like that. You would say negative 1,000
100x.
plus. Yeah. Or 100. It would be, I think in that case it would be 100x, but 100 times
yeah.
x. But that's just kind of to kind of show you that even if your starting value is negative, you can still have a function that will grow exponentially. It'll still get bigger and bigger. It's just kind of taking, if you picture that on a graph, you'd have something like this that looked, instead of starting up here and going this way, it would just look like this. It would be going up like the same way. Does that kind of make sense? Good. Okay. And then B, if B is negative, think about it like this. Remember when we talked about transformations of graphs, which we would have already talked about? Am I done?
Yeah, time's up.
Okay. Well,
Yeah.
yeah. So just flip it. So. things like that.
Thank you.
And then homework is a little fun worksheet. So I'll pass those out real quick. You can do with them what you like. And pass them down. All right.
Is that 15?
But good. So
Yeah.
feel free to come find me after
Yeah.
after school or open hours, and I'll answer questions. Thanks, guys.
And yeah, please fill out these forms.
Right now.
Yeah,
Do it now?
yeah,
Sure.
5 minutes. Yeah, we have 5 minutes
Do we have to return them right away too then?
Yes, because you have to move to other classrooms.
I didn't know. if we
Are those
were
going
gonna-
to me or are those going to?
No, I think,
Well, shouldn't we be able to keep them?
Yeah,
So we have to write
we have to
a
do a reflection.
reflection.
So I would like to have
Oh.
this.
Yeah, cause
Yeah.
I'm gonna put comments on it, I wanna look back on that stuff.
Dr. Shu said you guys have to submit today, right?
I don't know, she didn't say in class.
We
Did
could,
you think?
we could go find her and give it to her, she actually wants it.
Okay, yeah, anyway, we have 5 minutes to think about.
Okay.
And you can go to the next classroom.
That went so fast.
Yeah, wow.
Yeah, it did.
That went so
Yeah.
fast.
We only had like 9 classes. Like, oh, it's probably
Yeah, that's what I
really
thought.
big.
Well, when we went through the,
I think
like, after we came up with the equation, I was like, man, I probably still have like 15 minutes left. I was like, nope.
I know, it's crazy. Did you have like a clock up there you can see or?
No, well, since I went full screen, I had
Oh,
no
yeah.
clue. I was gonna freeze it and then get out of it so I could see it,
It'd
but
be nice to have a clock in here.
Yeah.
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 Cause I thought I was fine, I thought I was fine on time, but apparently not.
What do you have to align with state cores and standards, like, we don't know, I don't know them off the top of my head.
Yeah, actually, this part is about preparation, so
Like you didn't put any on the slide.
yeah, so it is hard to observe in the classroom, but sort of like you can find in the setup or
Actually, I'm gonna sit down.
oh, you don't need to.
I'm gonna do it on myself.
Yeah,
Okay.
just
Good to
on.
know.
But I think
Just-
just on your reflection paper you can.
Okay, so just kind of reflect on myself.
Yeah.
Okay. Darn, I was gonna give myself a perfect score.
I think you can.
Be harsh, guys.
I'm being pretty
Please do.
done.
Should we move on? I get this dude. No. Steven, you're this gifted student.
I was asking questions left and right, that's what, literally, like, that's what I was doing. I don't know, I really didn't know, or not,